Hey guys, this video is the third part to solving out our particular problem which we started with. And as a brief refresher on what our problem is and what we've done in the previous two videos, our problem was we've got two blocks connected to each other via a spring, and my question was what's the velocity of our block B when it falls down 2 meters? Right? And what I'm attempting to do is generalize the solution, so I'm going to solve the problem with variables and then I'm going to plug in all the values at the very end. Right? And in our first video, what I essentially proved, I proved that our blocks are actually moving, that the tension was enough to overcome all the forces pulling the block downwards, right? And in our second video, what I showed was, I kind of left you on a cliffhanger, I showed you this giant equation right here. And I derived that equation from our mechanical energy formula, which is delta E is equal to the work done by non-conservative forces. And as a brief refresher, this was essentially, this term right here, this beast, was just the change in mechanical energy of our block A, and this beast was our change in mechanical energy of our block B, right? And as a result, now this video is going to be dedicated mostly just towards the algebra of solving this particular problem. But before I get started in the algebra, it's really important to simplify a few terms. Like, what is y2a minus y1a? What does this equal right here? And what does this equal right here? Well, by now we should probably be fairly familiar with calculating these types of things. We know that we can create an axis wherever we want on our chart, right, on our particular diagram, and then all we're finding is the change in displacement, right, from your initial point to your final point, right? So let's first figure out how to calculate this one, y2b minus y1b. Well, let's think about it. If our block is right here, right, so it's hanging in free fall. This is the very start of our problem. If it's hanging at free fall and then it moves down a distance h, and h equals 2 meters in this particular case, and it falls down a distance h, right, that would imply that y1b, depending on where we place our axis, but let's say we chose to place our axis right here at our initial position. Let's say we chose to place it right here. That would imply that y1b would be equal to 0, which implies that y2b would be equal to minus h, right? Because if you think about it, it's gone down a distance h. It's gone down a distance h. That right there is h, right? So in other words, we could really say that y2b minus y1b is going to be equal to negative h minus 0, or just negative h, right? And I hope you should be familiar with this type of way of solving these types of problems by now, because rather than go through the laborious process of choosing an axis for calculating y2a minus y1a, I'm just going to calculate the change in height. So I'm just going to kind of zoom through it. So I hope you can stay with me. All right. Well, so we've calculated that this in the brackets term cancels out to minus h, right? Well, what's y2a minus y1a, right? Well, if our block is initially here, and it's on a slope, so I'll put it at an angle. If our block is initially here, and then it moves up a distance h, like I've talked about in previous videos, right? Then what's going to be our vertical displacement? Well, we know that this displacement here is going to be h, right? In fact, I should probably just draw one arrow. Our vertical displacement, our slanted displacement is going to be a distance h, right? We know that because the other block falls down a distance h. What's going to be its vertical displacement? Well, it'll move up a distance, and it'll move to the right a distance as well, won't it? And to calculate what component it moves up and how much it goes down, you need to know the angle, right? So you can use trigonometry to solve this. And we know that this angle right here is theta, right? And in case you're not getting this, let me scroll up to our problem. Essentially, we're using this angle right here. We're using this angle right here, theta. So if you imagine it, we're kind of just this is our block in its second position, and this is our block in its first position, and we're just calculating this height just here, this change in height from here to there. All right. Well, let's go down so we can view it slightly better. Okay. Well, now that we've got a good understanding of what we're trying to calculate, let's just do the maths for it. Well, we know by trigonometry, if this is theta, that means this is 90 minus theta, which would imply, because this is a right angle, that this is theta, right? Meaning that if you take if you calculate sine theta, you'll be able to work out this distance right here, which will just be h sine theta, right? H sine theta. It's just trigonometry. Alright, consequently now, we know that the displacement our block moves in the vertical direction only is going to be positive h sine theta. It's positive because it's moved up, right? As a result, this will cancel out to equal to h sine theta. And the positive and negative makes a big deal here, fellas, so make sure you get that right. Alright, well now that we've got that all sorted, let's see if we can actually simplify this expression right here. And I'm just going to delete this temporarily so that I can make room for what I'm about to write. Alright, well I've discussed previously that the velocity of our second block is going to be equal to the velocity of our first block, right? So that's this term right here. So all I'm trying to find is v2, right? And v1 for both blocks is 0, right? So this is going to be 0 right here, and this is going to be 0 right here. Consequently now, we've got a much more simplified expression, and let me write it out. We've got a half ma times by v2 squared, the magnitude of our velocity of both blocks, right, squared, plus mag h sine theta, plus a half mb times v2 squared. And this is the same v2, right? Because remember, the blocks have the same magnitude of velocity at any time because they're connected to each other. Plus mbg times minus h is going to be equal to minus mu k mag cosine theta. Well, that's a lot to write down, but at least it's simplified compared to what we had before. It actually fits on one page length, so that's kind of nice. Alright, let's see if we can simplify this even further. The first thing I'm going to want to do is factor out the v2's, right? So I'm going to do that real quick. And in fact, we can also factor out the halves too, so I'll do that. I'll factorize these two terms, this term and this term. Alright, and that'll leave us with a half it'll be a half v2 squared times by ma plus mb. Alright, that's these two terms figured out. Let's see if we can factor out anything else. Notice that a g and a h is common with every other term, right? So what I'm going to do is I'm going to bring all of the other terms on the right-hand side and factor out a gh. Hopefully we should be fairly comfortable with our algebra, so I'm going to try and push through this relatively fast. I'm going to leave, I know this term will now be positive because this is minus h, so that'll be gh mb minus, and now I'm going to bring this term across. It's going to be minus gh ma sine theta, and of course you still got this term on our right hand side, so that's just going to be minus gh mu k ma cos theta. And hopefully it should be a little bit more obvious now how I'm going to factor out the gh now that I've rearranged these terms slightly. Well, on the right hand side, we're going to get something which looks like this. We're going to get gh factored out, and it'll be turning into mb minus ma sine theta minus mu k ma cosine theta. Alright, but on our right hand side it'll remain the same, so we've got let's just call it v2 squared times by ma plus mb on 2. Alright, well, it should be fairly simple. I'm just going to multiply by 2 and divide by our total mass of both of our objects. So I'll be left with v2 squared is going to be equal to 2gh divided by ma plus mb times by this funky expression in here inside this bracket, which is going to be mb minus ma sine theta minus mu k ma cosine theta. Alright, rather than writing out the next step, I'm just going to square root both sides, so I'll get rid of this squared sign and square root both sides. And we're done. Right, this is about as simplified as this thing can get because none of these terms are common. Right, consequently, this is our answer. Right, this, v2, will denote the velocity of both, the magnitude of our velocity of both block A and block B after the block has fallen down, after our second block has fallen down a distance h, right? Consequently now, this becomes a matter of just subbing in particular values, right? And if you'll recall, our values right here are just there. And I'll even write it down here. And copy it for you. Oh well, I'm having problems copying it, but really you can see the values just there. Essentially it becomes a matter of plugging them in at this point just to solve our particular problem. And I've done this problem before, so I'll just tell you the answer. But essentially it basically means that our second block, the magnitude of our velocity of our second block, once you plug in all of these values, right? So once you plug in all of this, is just going to be equal to 3.40909 meters per second. I don't want to go through the tiresome process of plugging it into this formula while I'm kind of recording. It would be a waste of time. But essentially, this is our answer. This is our magnitude of our velocity of our second block. But if the question didn't ask for the magnitude of our velocity, it asked for our velocity, right? So we need to use a little bit of common sense to figure out which direction it's going to be facing. Right? Well, just think about it. If the block's moving down, that means the velocity is going to be moving down, right? I hope you can see that. If this block is sliding vertically downwards, right, that means that your velocity is going to be in your negative j direction, right? Which implies that v2b, your velocity of your second block at your second point, is going to be equal to minus 3.409 meters per second in your negative j direction. Alright, and it's negative j because it's facing down the hill. So that's your answer. Alright guys, that was a really tough problem. Most problems won't get more tough than this in the particular videos that I'm going to be doing, but I hope that made sense, and I think that's probably going to be the end of all the videos I'm going to create for this particular topic. Sooner or later I'll get started on circular motion or potentially another topic. Thanks guys.